Hello, welcome to a new video. So in the past few videos, we've kind of looked at the reference DeepSeek v4 implementation, and now we're going to get back into inference land. So in particular, now that we have a good understanding of the model, let's figure out how you would implement it in something like vLLM. But before we actually dive into the pull request that implements it, let us build an intuitive understanding of how vLLM integrates its page attention mechanism with models. So at a high level, the flow is as follows. Before a vLLM calls forward on the model, it will call this with set forward context manager. And then within the forward, it's going to call this DeepSeek v4 attention custom op. And this custom op is going to call get forward context, which gets the state that's set in this context manager. And this state is going to basically give you pointers into the KV cache where you should read and write from. So let's go through a concrete example. Imagine we have the query, the quick brown fox. So as we know from past videos, the first thing we need to do is prefill. We need to basically generate KV entries for each of these 4 tokens. Now, conceptually, what is a KV cache? A KV cache is just going to be a large contiguous block of memory. But as we've seen in prior videos, vLLM effectively creates an allocator to manage the memory in this contiguous block. So when a request comes in and we need to do prefill for these 4 tokens, we first talk to the scheduler and we say, hey, can you give me enough blocks to be able to write 4 tokens into? And in this case, imagine we have a block size of 4. You only need 1 block. And so it will give us back a physical block that we should write to, in this case, physical block 5. And then we will record in our metadata block table, request 0 maps to physical block 5. So once we have the physical block, we can actually do some basic arithmetic to figure out the absolute index in the contiguous tensor representing the KV cache, like the indices that we should write to. So in particular, for physical block 5, it's 20, 21, 22, and 23. And we can basically use this in our kernels to tell the kernel, as you're calculating the KV entries, where to write into the KV cache. So once we're done with the prefill, now we have this physical block all written, and now we need to decode. So as you know, for decode, we also need to calculate a KV entry for the next token. And so now all of a sudden we need 5 tokens. And so we go back to the allocator and we say, hey, we need a new physical block. And in this case, the allocator gives us block 9. And so now in our block table, our request 0 corresponds to 2 blocks, 5 and 9. And then similarly, we can calculate the offset. In this case, it'll be 36. We can calculate the KV entry for this new token, and we can write it here. And then lastly, because we know the sequence length and we know the block table, in our attention, we can basically say, hey, these are all of the memory addresses for the KV entries you need to attend to. In this case, it's 28, 21, 22, 23, and 36. And then you can do the attention. So hopefully that was useful. It was useful for me to kind of build this bridge between what we were just looking at into the pull request we're about to look at. So hopefully that was helpful, and I will see you in the next one.